Hello and welcome back to the Fullerton College Pre-Press class. This is Professor Ben Hewitt. Today we're picking up where we left off in the PIA's Pre-Press Trainee Manual, Section 6.3 Advanced Output. This is video 2 of hopefully 2, but we'll see. We're talking about spots and gray levels and how gray levels control your ability. Actually, they don't control your ability. Gray levels are your ability to control the tonal range of a reproduced image. And the ability to reproduce the tonal range of an image is also your ability to control the color mix. As process color deals with ratios of multiple colors of separation, each color of ink, your ability or your machine's ability to control the amount of ink that goes down and how fine a step you can do determines how closely you can match color, as well as how well can you just create tonal range. Because tonal range on its own is black and white, but tonal range times 4 separations determines how accurate and how many colors you can hit. So halftone dots should be able to show lots of different sizes, not just normal 1 to 100% integer numbers. So the number of spots used to build the halftone dot is what makes you, or what generates the number of gray levels you're able to achieve. So the best quality output uses a cell for each halftone dot that's at least 16 by 16. And that means it's a grid of 16 by 16 pixels, and those pixels translate into laser spots when the plate is imaged. Or if you're talking electrostatic printing, 16 by 16 for when you drop down that individual fleck of toner. Anyways, you get 257 different shades of gray doing this, called gray levels. 0, nothing, and 256, completely covered, are also available, as well as 257 as well as 255 intermediate steps. And all of that amounts up to the ability to do that many gray levels. Each distinct level of gray from a grayscale file, since grayscale uses a single channel on a computer, which allows the single byte of information to control it, allowing you to have 256 levels of gray in your print file. This means that a grayscale computer image can be accurately reproduced using a 16 by 16 spot grid to create the halftones. Let's look at this from here. So here's a high resolution output set at 150 lines per inch. Remember, the lines per inch is double the dots per inch you would normally get. So 2400 DPI is talking about the length of the individual machine pixels and therefore individual laser spots when it images the plate. Each one of them is 10 microns. And 150 lines per inch, each cell can be made out of 16 pixels wide by 16 pixels high. If you multiply those together, that gives you the 256 possible spots or squares to fill in or not fill in. And again, each laser spot covers one machine pixel grid. So if you do your document using the same LPI on different devices, you get different gray levels resulting by the interplay, or the ratio really, between laser spots and halftone dots. Down below here, and you'll see in your book as well at home, is a small little chart of different things. A typical high resolution, which is really kind of standard quality actually, output of 2400 dots per inch at 150 LPI gives you that miracle, that beautiful 257 gray levels, which is great. Now, if you only have 600 dots per inch and you're still going for 150 LPI, well, then you have 17 gray levels. It's pretty low, isn't it? 17 gray levels is not much. If you have 600 DPI and you're going for only 106 LPI, you get 33 gray levels. And if you're using 600 DPI for an 85 LPI halftone grid, you are going to end up with 51 gray levels. So that is typically done for flexo printing, which often will use only 85 LPI, which gives you 160-ish dots per inch effectively. physical media as opposed to more chemical media such as offset printing. So physical media like letterpress and flexo, things that need to be done as relief printing, typically have a lower resolution because those very fine dots have to exist as physical little tiny sticks that stick up in the air, and only the tip of that little cone of each one of those sticks is a halftone dot. So it has to be thick enough and robust enough to stand up under the pressure when you press the paper against it. So anyways, those would be 85 lines per inch. And so if you did that, you could eventually effectively print that kind of unwholesome book series, couldn't you? 50 Shades of Grey. Turns out they were printing it on 85 lines per inch using a 600 DPI output device. That's where those 50 shades are coming from. So DPI does change your gray levels. Here's a picture of what we were talking about. We're going to 150 lines per inch no matter what. So both these things are scaled to the same size. Assume that it's 1/150th of an inch for the overall square in which the grid is contained. On the left, we have our 256 gray levels because it's 16 by 16. But on the right, using only 600 dots per inch, we now have 4 by 4. So there's only 16 spots in that grid. And 16 spots, including the option to leave them all off, gives you only 17 levels of gray. Let's look at the math on this for a moment, because yay math, right? So if you're able to image halftone dots, it's easy to calculate the gray levels with some simple math. Down below, it shows you what you're doing. So you divide the resolution by the LPI, square the result, and add 1. Let me go through that a little bit slower. First, to figure out how many squares or how many machine pixels you can give per halftone dot, you're going to divide the total number of machine pixels per inch, the 2400, by 150, for that's how many lines per inch of line screen you're using. That gives you 16. That means you're going to have 16 squares in a line making up, 16 squares make up each one of the 150 squares that make up the 2400 total number of dots per inch. So 16. You square that, so 16 times 16, that gives you our magical computer number of goodness, 256. And you add 1 more to count for the completely off level, to account for 0. And that's it. So 2400 divided by 150 gives you 16. You square it to give you the grid because it's length times width. Then you add 1 more for the all off thing, and that gives you the 257. Spot size. So the laser beam, the thermal head, the inkjet nozzle, whatever it is making it, likely probably only has 1 size. That's standard. Inkjets don't make different size ink droplets. Laser jets don't do individual size toner flex. They only have the 1 size. And a lot of times the lasers that image plates only have 1 focal size. There are a few very rare, at least in my experience, I've never seen one in actual use, but you do have some more high-end machines that are capable of different sizes. And that does make them more adaptable for doing different line screens of output. Typically, they're kind of set in their ways, and whatever it is set up for, it's good for, and what it's not set up for, it is not good for. The diameter of these spots are measured in microns. A micron is a millionth of a meter. Yeah, sorry guys, it's metric. And we're still converting millionth of meters over onto dots per inch. Yeah, it's a little tricky sometimes. How are the dots created? Here's some fun stuff. Let's talk about screening the dots and what they do. There are 2 types of screening. How they're created isn't quite the right word here. It's more how are they arranged? Where are they in relationship to each other? And how do the dots control the tonal range by covering or revealing more of the paper beneath? Just like old school radios before people got all digital, you had 2 types of screening. I got called screening on a radio. Radio, we're talking about the radio wavelengths that are being picked up by your car as you drive, because that's one place you will still listen to the radio. Not so much in your living room tuning into this week's radio drama. Not anymore. Anyways, you have AM and FM, the 2 little switches on your radio. Just like that, that's talking about the same concept of how you are arranging these dots. So we'll get to there in a bit. First, when you rip a file, two things happen. First, it rasterizes, then it screens. Rasterization is taking everything in the PDF, every little bit, every graphic, every picture, every effect, every piece of text, and converting it into pixels. That's called rasterization. A raster image is an image that's been completely converted to pixels for output. Here's a picture of rasterization. On the left, we have vector objects. Nice, clean vector. On the right, it has been rasterized and turned into pixels because in the end, all output devices output pixels. The best thing about vector is that it doesn't turn into pixels till the very end. The best thing about PDF is it waits even longer to convert to pixels, but it still ends up as pixels. Once you've rasterized, then you screen. The resolution of the raster image already depends on the device. Each RIP will have its own resolution, which is ideally, not ideally, which is paired to an ideal resolution to work with its output device. So if you're talking about a digital proofer, you're looking probably at 600 dots. Apologies, I had something in my throat there. 600 dots per inch is typical for digital proofers, although now 1200 is a little more useful, more usual as well than when this was written. And a plate setter is typically around 2400 DPI, which means its raster image is going to be 2400 DPI. The point is not what the DPIs are of these various devices. The point is that they match the output of the machine. Here's a picture over here. The raster image on the left that we created from the vector image on a previous slide is now being screened on the right here into halftone dots. You can see that it looks a lot fuzzier, and it kind of is. The mixture of the colors that make up that off yellow, off blue, and off red are all different amounts of and combinations of how much cyan, magenta, and yellow are mixed together to make them. In the bottom right of it, the biggest triangle of this image, the reddish color is primarily magenta and yellow. So there's spots of magenta and yellow. Depending on how much magenta or yellow you want is how big the spots are. Less magenta or less yellow means smaller spots. You can see that as the magenta tapers off to near nothing inside the yellow. Likewise, the cyan in the blue area is very much heavy set, and then when you go towards the yellow part, there's almost no cyan in that color, so it's just a few very small dots. That is, however, an example of AM screening. Just like how the radio deals with its radio waves and its signal, so do we work with our screening on our output for halftones. AM screening, amplitude modulation. That means that what you're changing is the size. When you're talking about radio waves, if you want to go old school on the AM radios, that means you are transmitting a wavelength that is the same size. I'm sorry, my mistake. Whoop. That means that you're transmitting on the same frequency of how often the waves come, and to determine what you're transmitting, you change the amplitude, the size, the wavelengths, not just the frequency of the waves, but how long the waves are. So that's AM for radio. AM screening means all your halftone dots follow the same strict square 90-degree perpendicular, although it might be rotated completely, but not individually. The whole grid can be rotated, but it's still a grid. They stay the same size. Sorry, they stay in the same places, but the size changes. My favorite example of this is, imagine that you have a marching band marching down the street. Maybe you're watching a parade on TV, and you see in that band different size people playing different size instruments. You have the little 30-pound flute players marching in the front. Somewhere in you have the clarinets, and they're only for show because you never actually hear those things. Behind them, you have the trumpet players and the saxophone players, the trombones, and finally the big guys playing the huge sousaphone. Tubas, and behind them, the drum line, starting again with the small snare drums, and then the quads, and the bass drums of various sizes. And all these different size people playing all these different size instruments are all marching in the same grid. The files and the columns of the marching band are always the same, no matter how big the instrument or the player. So the part in the back of the band, where the tubas and the bass drums are, the people and their instruments cover more of the parade. When you're looking at it from above, you see less street through them because they're bigger, and therefore closer together. Even though the middle of each person is farther apart, the bigger person carrying the bigger instrument takes up more space and gets closer to the people next to it. AM screening is the same thing. The dots get bigger. They never break formation. They stay in that grid, and they get bigger when you want more color, and they get smaller when you want less color. The spacing does not change. And you also have to align these into a correct pattern to avoid a moire. A moire is when two things don't quite line up and you see weird patterns and weird shapes that don't really exist but are there because you see them. If the video worked, I would show it to you right here. Anyways, the angles are yellow's at 90 or 0. You can barely see yellow. Yellow's harder for us to pick up and it's not very intense of an ink, so we let that one sit on a normal grid because you're not going to notice as much. Magenta's tipped to 15 degrees, cyan to 75, and black at 45. By screening all these at these respective angles, they don't create an interference. They don't wreck your vision of the picture you're looking at. In fact, they make larger dots. They call those rosettes. It's a larger circle made up of the smaller halftone dots. I know this video is getting a little long, but we can finish in only 2 if I carry on for another minute or 2 because we're almost done here. FM screening. This stuff's a little more advanced. It's more recently developed, and it takes a better computer algorithm to be able to do this. FM screening is frequency modulation. The dots stay the same size, but their distance and locations change. Same goes for FM radio. FM radio is using the same frequency the same wavelength no matter what, but the frequency of those waves keeps changing. And that's what's also happening here. No matter what, the dots are the same size, but they're closer together when you want darker colors, and they're farther apart when you want lighter colors. The nice thing about this is it does some things for you that the other one can't. When you get into very, very subtle light colors like pastels and lighter flesh tones and highlights on skin, this sort of thing will do a great job of not wrecking it by showing you the dots. When you have a heavier coverage and using AM screening, when the dots are all closer to 100% and they're thicker and heavier and therefore appearing closer together, or they're closer to touching even though their positions don't change, you don't notice them as much when there's more coverage. When there's less coverage on an AM screen, you start to see, hey, there's a grid there in that light area in that guy's eyeball on that picture. Why is there dots there? And you start to look at those. But with FM screening, because you're using the smallest size dot no matter what, when you get into the lighter areas, you have a more even coverage and a much better, more subtle look of shading. FM screening is not good for everything. If you're creating more like graphics and less like photos, AM screening is actually better for creating graphical backgrounds. If you want to have like a grayish tone behind something, it's better to set up that gray by having a grid of black spots the same distance from each other rather than a random area of black spots kind of floating around, because they have their own kind of look. And the image here shows you kind of what FM screening looks like. Now, the very best plate setters being made now, well, they do the Mission Tortilla Girl thing, and why not both? ¿Por qué no los dos? They do both. For graphical areas and areas that would look better with AM screening, it uses AM screening. And when you get things that are in those light pastel-y, earthy or fleshy tones that really want to be done with FM, why? It uses FM instead. Those are extremely cool and extremely expensive. Anyways, that's it for this week. Thanks so much for listening. Sorry this video went a little bit long. I appreciate your patience.